what I had planned was to discuss the HRNet paper, and also Rekul, if you wanted to share. I don't know whether we got a chance to go through the ideas that you had of combining various different concepts from the papers we have discussed, so we can do that following discussion of HRNet.
Yeah, I just had only one implementation that I had going. That was the unit with the dilation stuff, and yeah, I haven't really got to implementing anything else new, so nothing much from my side.
Okay. Anything else, Steve, Mehul, Joseph, anyone else online wanted to share?
I haven't done anything on Steel this week, so I haven't had a chance to progress this at all.
Okay. And before we get going on the agenda, I think just as a context setting, I sent out a few messages soliciting, inputs for the next competition. I think we discussed, and multiple people did offline sent me messages saying we've done a couple of images, so maybe we can give a shot for NLP. So based on that, I kind of put some thoughts on a spreadsheet of recently ended NLP competitions. But if you have other ideas that or competitions that I have missed, please feel free to include them. Also, for context, since there have been a lot of discussion, some of you may have seen it on different channels. Some people, for whatever reasons, cannot join the Saturday call at this time. So for that reason, and also there was a desire apparently to start NLP only focused Kaggle group. So that's apparently starting up on Mondays. And there was an NLP projects group that is ongoing, and one or both of them, I don't believe the Monday group would be interested, because they specifically are doing this since they some of them claimed they couldn't attend the Saturday sessions, and they'll be only focused on NLP competitions. My interest is also, I assume several others, is in keeping this Kaggle group more flexible and moving on to different things. It could be a combination of NLP and images we tackle next, or image tabular and NLP. And so this group will continue. The NLP projects team is likely, or members of that group, if you will, are likely to join going forward for the duration that we would be doing NLP competition. So that's kind of some background context before we get going on this week's discussions. Any questions regarding that? Okay, if not, sorry, was there a question?
So there's going to be like 2 new groups or just 1 new group?
No, the NLP projects group was always going on. That was kind of parallel or simultaneous to this meeting. I believe the focus of that group was to share projects that people are doing in the NLP space. But Darren, who runs that group, is actually email exchanges or Slack exchanges, and he himself and he's suggesting to members that if multiple of them are interested in doing an NLP Kaggle competition, then they can join us for the duration that they would be doing NLP related Kaggle challenges. So that's been going for a while, but there were different people joining and discussing, I think, their work on various NLP projects.
Okay.
Okay, so with that, let's see. Let me see whether I can first bring up, give me a second while I try to bring up the HRNet paper before I share my screen. Okay. Are you folks seeing the paper yet?
Yeah.
Okay, so just to give context to anybody who's joining us, I think regular members have the context already, but there's a third of the papers, if you will, that we're discussing, which has published or based on which some state-of-the-art results have been published on semantic segmentation. The first two were pyramid networks or TSPNet and various versions of DeepLab v3 plus all the way up to, or DeepLab v3 and its various versions all the way up to DeepLab v3 plus. So this is kind of the final paper on that front that we'll discuss today. And if we can wrap that discussion up, then I think starting next week, we'll discuss what next competition we'll move on to. Okay, so this paper, I'll just go through. Please feel free to chime in with any explanations and or clarifications. Bottom line, I think this paper, at least I felt, was much better written with more images, easier to understand than the DeepLab paper. The TSPNet was again comparable to this one. But the basic idea seems to be that in dynamic UNet as well as in DeepLab and TSPNet, they connect high to low resolution streams at multiple points. And in this case, why not do it in parallel? And also, I think the other key idea is do it repeatedly, not just at particular points like UNet does. And that leads to the semantically richer and spatially more precise, which I thought was interesting as well. So as many of you who have done this many more times than I have are familiar, I think the standard approach is to go to a high resolution representation, and that's needed for semantic segmentation, post-estimation, object detection and stuff. And this HRNet, which stands for high resolution net, the idea of the key contribution is that it's able to maintain the high resolution representation throughout the whole process. And actually, give me a second while I also bring up a whole set of other links that I bookmarked. So I'll do that on the side here for a minute. Okay, let's switch to that. Let's start with that. And moving on, I think the key contribution, as we'll see in a minute, is this multi-resolution fusions by exchanging the information multiple times. That's why they talk about over and over. And the other aspect is it connects the high to low resolution in parallel, not in series, and so it's able to continue to maintain high resolution. So rather than talking about it in theory, let's also look at this particular image, which conveys the major idea, which is that a high resolution image, which is this top yellow block that continues to go through all the way to the very end. So that's in parallel to, and then you get a somewhat reduced resolution that goes in parallel all the way to the end. And then again, after a certain number of convolutions, you reduce the resolution, and then that goes through, and then yet again, the smaller resolution, and that goes through. And then in the end, these things are actually, I take the back, the high resolution, let's say high, medium, small, and then smallest. The high and the medium resolutions are combined, as you can see. And then the high, medium, low are combined, as you can see. And then the high, medium, low, and the smallest, if you want, all combined. So that's kind of what is explained here, that the approach connects high to low convolution spans in parallel. So the parallel refers to the fact that these streams flow in parallel through the pipeline, if you will. And so that they claim, and it's kind of, I think, intuitive, that that helps maintain the high resolution and helps not having to recover, which is what we do in UNet, because in UNet, if you recall, what happens is somewhat like this. You go from high resolution to small, and then you go back up again, and then you feed from one to the other at specific points in time. But that's not what they do here. They take it in parallel, and that the key thing they call attention to is the fact that the representation is spatially more precise. That kind of makes sense because you carry the high resolution stream all the way to the end, and then you just blend or recombine at different points. The fusion, as they call it, not recombination, but fusion. And then most existing fusion schemes aggregate the high resolution, low level, and then the high level representations obtained by upsampling the low levels. Here we repeat to boost the high resolution representation with the help of the low representation. And so they claim that the high to low resolution representations are not only spatially more precise, but they're also semantically strong. By that is meant, the particular details that are available at the high resolution, the semantics are continuously available while the spatial resolution is also kept high. Then they present two different versions, but the one which would be more relevant to the problem at hand of semantic segmentation is the HRNet v2, which combines the representation from all the high to low resolution parallel stream. And by that, again, as a picture, if you wanted to look at it, it is this D. So in HRNet v2, in HRNet v1, you just take the high resolution image convolution stream. B, which is what is relevant to what we'll be discussing, which is semantic segmentation. Here you concatenate the upsampled representations that are from all the resolutions. And actually in code, as we'll see in a minute, or in a few minutes, there's also a one-by-one convolution applied, but that's not shown in this diagram. But you can just think of only recombining, if you will, the high resolution, the medium, the low, and the smallest. As I have just termed it, you can call it different things if you want. But bottom line, what is being referred to is the fact that at multiple points, you're sending and recombining if you just focus on this last diagram, you can see that you're recombining different resolution images in this approach, right? So that's what HRNet version 2 does, whereas version 1 was different. And version 2 is where they get the best results for semantic segmentation. So that's what this particular paragraph talks about. And then, as I mentioned, HRNet v2 they show is better than HRNet v1 in semantic segmentation. And I think it's kind of interesting that they do get better and dramatic improvements for small objects. I would say intuitively one would expect that, given that they retain the high resolution image, which is a key contributor to that. So the related work and I think this other very fascinating aspect of this paper is, I think it's has a ton of references. So I think if you follow the references on this link, you'll kind of be familiar with state-of-the-art work in semantic segmentation. There are a lot of them. The one other aspect they call attention to is the fact that other mechanisms, and I believe we saw this, maybe others recall, I don't recall off the top of my head, does DFlat v3 plus begin to use match norm, or v3? One of them does, but the other two don't. I think the original one did not, if I recall correctly. Anybody recall that?
Yeah, I think v3 or v3 plus introduced that and spoke about it. I'm not sure which one though.
Yeah. So they claim that, do you recall whether HRNet used patch norms?
Again, the implementation that we see, we saw it, but I think the original didn't use it. I'm not very sure in the paper.
But the one that FastAI has uses it?
Yeah, because I think, Jeremy, nowadays when you say a conv layer, it's con batch norm relu by default. So
okay.
it includes batch norm in there.
So I think they call attention to that because that's not always the case, and we believe that it does contribute significantly. And then we compare to HRNet and Signet, which obviously combines the low to high, but it does so at specific points. Even as I say that, I think even in this case, we combine at specific points, but I guess it's the combination of two ideas, carrying the various resolutions forward in parallel and then combining it at multiple instances from low to high, because I think HRNet does it, but it does only at the matched and at particular layers or levels. Here again, DFlat comparing to DFlat v2 or v3 fuses the pyramid features obtained by pyramid pooling, and here their multi-scale resolution fusion module resembles the two pooling modules. And again, if you wanted to play with multiple ideas, I was also thinking you could do 8 convolutions and then fuse them back again too. Although I don't know whether, since you're carrying forward the resolution, whether that would necessarily help or add anything new. But one other idea is, the DFlat v3 plus paper does this depth-wise, and you could potentially add the depth-wise convolution idea here, thereby reducing your computation somewhat. So that's yet another variant you could apply to HRNet if you're interested in lesser parameters than even what HRNet has, or reducing your computation. So in this case, they say our fusion outputs 4 resolution representations rather than only 1, and they're repeated several times. And the 4 comes from these 4, and the fact that it says it's combined multiple times, if because it's combined or fused here, and fused here. So it's fused multiple times. So this is a discussion of their approach. It connects high to low convolutional streams in parallel. So that's what this is, the parallel. So high to low. So this high resolution makes it low and then takes both of these in parallel. And then this is the fusion part where it combines these multiple resolutions back and then creates a yet another lower resolution version. And they talk about the difference with respect to their first paper. As I said, it's, in the first paper, I believe they just took the high resolution. In this case, they take all four. And then they also explain, as we see in a subsequent picture, how they believe that fusing different sized, different scale resolution back as they do in this picture or in this picture is equivalent to full convolution on the high resolution image. And that I thought was also interesting. Then these are the details before we get into this particular image, if you will, or and so on. They do a stem, which is essentially a pair of 3x3 convolutions of stride 2. So 2 stride 2 3x3 convols, which help reduce the resolution to 1/4. And then the rest of what they have in the code outputs whatever the input resolution is. That is to say, you take the input image, go down to 1/4, and then your output is 1/4 of the actual input, because the output is the same as what you input after the stem is executed on it. Then, in this case, they just explain what is going on. I think recollect the code, and I kind of also bookmarked that. And let me see whether I can combine the windows. Okay, maybe now I'll get to it in a minute. It's a different window, so without confusing people, let me keep going and then I'll switch in as you ask me. So here they just try to provide the details of what is happening within the image. So the fusion module aggregates the information for these high, medium, low resolutions. And it's stride 3x3, it's a stride 2 3x3 convolve, which is then followed by an upsample, and that's a bilinear upsampling followed by a 1/1 convolution. So that's what these different blue, green rectangles represent. So when you are combining, when, for example, you're going from this orange block to the yellow block, in between is a blue rectangle, which means that you upsample and then follow it with, it's a bilinear upsampling followed by a 1/1 convolve. So that's what is happening here. Again, here, when you do this, you do bilinear upsampling followed by a 1/1 convolve. And then when you go down, then it means that you do stride it 3x3 in order to bring it down to a smaller resolution. So that's kind of what is happening within each of these pieces. You don't these arrows are not direct. They actually involve operations when going from, say, an orange block to a yellow block, or from this pinkish block to the orange block, or from whatever this color red is to the various values. And then if you're going downwards, as the down arrow indicates, then you're doing strided 3x3 convolves in order to get down.
One thing I didn't quite get was if the two-strided convolution downsample the higher representations 2 or 4 times, by 2 or 4 times. When he said that 1/4 resolution over there, I'm not sure. Yeah, what's the downsampling scale or the rate?
It depends on which particular transition or translation or you want to go through, Antonio. Meaning by that, what I mean is, for each level down, you do a 3x3, and then so if you're going from the yellow, let's say, to the orange, then you do because that's a 1/4, and therefore you would do the strided 3x3 once. But in order to go from the yellow to this, whatever this color is, pink, let's say, then you have to do it twice to get it to 1/8. But if you go from orange to here, you will do a 1/4. So you would do only a single or a set of 2. Right? So it depends on from which level you want to go to which level, and how many strided, two-strided 3x3 convolves you do. Does it make sense? Meaning, if you want 1/4, you would do a single two-stride 3x3 convolve. That would take you from the orange to the from the yellow to the orange, or from the orange to the pink, or from the pink to the red. But if you want to go from yellow to the pink, you would do that twice, because here you're not going 1/4, you're going 1/8.
1/6.
Okay, got it. So the bilinear are also like 4 times or 8 times, depending.
Yeah, yes. That's right. Sorry, Ricky, you're saying something?
No, I was just saying, like, if you do a stride 2, though the 2 is there, you're actually reducing resolution by 4, right? Because you're reducing height by 2, width by 2.
Correct.
That's
so
where your resolution.
That's why I said. Sorry, go ahead.
No, that's what I'm just saying. That's what the resolution drops by 4. And then every time you go down, I don't think it's 1/8, it'll be 1/16, though, right?
You're right. You're right.
So that is the measurement there. And I think a key point that I really had to kind of go back and understand was, why is it that when you're going down, you choose stride 2, but when you're coming up, you're doing bilinear upsampling? I mean, both of them can be like interchanged, right? You could even do like, you could learn when you're going down and not learn when you're coming up. And I think he makes a key point somewhere there saying that you can put learning parameters on both the ends, but while going down, you potentially are like learning some representation, you're losing information, right? So you want to learn how you are losing information kind of in the most efficient way. Whereas when you're coming up, that is upsampling, you potentially can never add new information to yours because you don't have any more information to add. And that's why they say that they choose to upsample over there, which I thought was pretty interesting. So just wanted to kind of bring that out.
No, that's very, very interesting.
That was a great observation. I believe he also said that oh, sorry. I was going to say that he also said that I think it was on another presentation. He said that he did experiments with those pixel shuffle and deconvolution layers to learn upsampling, but they didn't get any substantial improvement. So they kept on with bilinear interpolations also. Maybe that's what Rakil said. I think what Rakil said, what an explanation for the phenomenon.
Right. Yep. Yeah. So I think the trade-off, more parameters versus the gain in accuracy was not worth it. So that was just the reason. Yep.
But one thing I was wondering, Rakil and Antonio, is yet another variant of this would be to try and do the Icnr and with the special initialization on the way up and see whether that improves even further the pixel-wise representation, because that's the closest I have seen when you come up how best to be most faithful to what you see at the low resolution, rather than just doing a bilinear, because what I saw in the discussions that Jeremy did was you get these, you remove the blurring effects of bilinear upsampling best by doing the Icnr with the special initialization, which is what he does in the HRNet implementation to improve the pixel-wise representation faithfulness to the original high-resolution image on the way up. Does that make any sense?
Yep, right. I think Antonio was just mentioning that the author did try pixel shuffle, but the trade-off was not worth it, I guess, or whatever the reason was. But yeah, squeezing that in would be a good experiment.
Oh, Antonio, so you said he tried pixel shuffle along with the bilinear upsampling. You heard him say that somewhere else? Is that what you mentioned?
It's a bit unintuitive because we think that the pixel shuffle and those learning upsampling layers should be better, should get better results, right? Because they're not blurry like bilinear interpolation. But on the experiments, he said that he didn't get any improvement on the final ending task. So maybe
interesting. Yeah, but that's, you know, it goes back to many times I've seen that what people vouch for in machine learning in a particular context and for particular competitions and for particular data set don't generically hold true. So,
yes,
you know, that's why the field is much more empirical than many other domains, meaning unless you try it for the data set, for the conditions that you're trying to implement, you can never a priori say, oh, this will help. We think it helps, but in this case, what you're saying is it didn't, the author said, hey, it didn't seem to make much of a difference.
Yeah, I agree.
And I think your point, Rakil, is an excellent one. So you're saying that somewhere he mentions in the paper that while going down, we lose information, therefore we try to, I don't know that we can say recapture exactly that, but at least try to capture some of it through the convolution and learning the convolution parameters. But when we're coming up with, you know, it's not like we can, I mean, we try to generate new, but it's not, we can't do as good a job of generating fresh information from less information. So there's not much point, which kind of then also strengthens this, hey, why Icnr and other things don't. But if that was generically true, and this is the problem I have, if that was generically true, then we shouldn't have seen the benefit even when Jeremy applied it, but we did see the benefit in those papers.
From my quick recollection, I think the author said it did help in improvement, but I think it was that the trade-off of adding those extra number of parameters versus the gain in percentage was not worth it. So that was just a decision.
Not worth it. Okay. That, but then, so that's where I guess the precision, the results they saw in mean IOU may not have mattered, but maybe, you know, if Jeremy had, oh, look how pretty the pictures are, or how accurate the pixel representations are and not blurred, then it matters because it was a subjective and not a MIOU method there.
Probably, yeah.
So I guess the metrics of comparison matter as well. Interesting. Okay. Moving on. So I think the other element, and I'll just touch on it here and we'll discuss it more, I think, subsequently, is what I thought was interesting was if you see the stack that is built up here, typically in the other papers, I've found that, you know, since anyway they do a one-by-one convolve following this stuff, here they say followed by aligning the number of channels. But if you see this image and also subsequently, they seem to say that they only align after the fusion is done. And we'll get into that. And that I thought was an interesting difference as well. Because if you see this picture, and I believe it is accurate and not just an error, the width of the thickness of the stacks is not identical. So these four don't have the same number of channels. The thickness is different, as you can see when they are stacked together. And that I thought was interesting.
Doesn't that just follow the general convention of any encoder? Like even a ResNet, as you reduce width, that's why you increase number of channels, right? Width and height.
Yeah, no, but the one-by-one, you know, like for example, I forget PSPNet or something, like as soon as you do one-by-one, you tend to make them all the same, right? After following the one-by-one. In fact, you do the one-by-one in order to get them to be the same. But in this case, I saw that they are not necessarily the same. I understand. Go ahead.
No, I think if I'm not wrong, if last time when we saw the code, the way we wrote the code was we said, okay, if NF is the number of output filters in the PSPNet or the ASPP module, let's see that each of the parallel branches give out NF by 4. Let's say if there are 4 branches, right? So we kind of regulated what the output number of filters here that in direct comparison basically to the depth of the channels. So I think there it was more of a control choice that we made. And the difference there was that we stuck this PSP module at the end of, let's say, the ResNet encoder, right? Here, the difference kind of creeps in because you're doing everything parallelly. You're keeping the high resolution, medium resolution, parallel resolution. So each of them have these extra number of depth axes. And now when you do the fusion, you still have those extra number of depth axes. And so you really don't want to lose information by chopping them off or doing something weird. So I think there's the difference between how we did it in PSPNet versus how we're doing it here is mainly because of how we have these parallel lines versus there it was kind of a series.
So, so to recap what you're saying is that this I get it in my brain is saying that in the case of PSPNet and others, we created the NF and made them equal. Here, since we're carrying the multiple resolutions forward, they just happen to be whatever they turn out to be. And you know, as he shows, they turn out to be C2, C4, C8, C for these 4 things.
Right.
And we just concatenate the C2, C4, C8, C and get 15C, and then do something else to them. So we don't, is what you're saying. So we apply, because he does apply a one-by-one at the back end of this stack, and we'll get to that in a minute, but he doesn't do it along the way. And whereas in PSPNet, these seem to do it along the way, and that's what I thought was different. But then my question to you would be, why would we not let the NF be whatever the NF turns out to be if we wanted to retain that information in PSPNet as well, and then do a follow-on one-by-one?
So the difference, if you look at the figure, let's say any of them, A, B, or C, PSPNet or DFlat would probably stop the encoder chain, maybe let's say the orange, right? And from the orange we will stack on the ASPP module, or you would put that PSP, the pyramid pooling module there. So now you're starting only with orange. So you have only those many number of channels. That's your width, that's your height. That is your starting point over there. And that is where you control NF by 4 or how many other pyramids how many other parallel paths you're taking out of that. In this case, you already have all these there's really all the 4 are pretty much your starting point, right? When you're trying to fuse it back. So you have all the 4 here, and that's the way I kind of see the difference between that and this. Like, I don't know if that makes sense.
I see. So that's why carrying forward the parallel parts is a key contribution or differentiation of this particular approach compared to the HRNet or DFlat based things.
Which is kind of, again, critical if you ask me, because you have these cross connections, right? And the cross connection unit pretty much do something like a fusion. If you think
right.
At the end of the day, if you look at that, HRNet is not like 10% or 5% greater than what a unit would give you. So it's kind of a different.
Yeah, I mean, that is something you do observe repeatedly, right? It's just like by a few points, and how much do the points really end up mattering is, I guess it matters to get your paper published, but.
Right. In terms of parameters and how fast it trains and all that kind of stuff, when you, I don't know, like nothing is like, I mean, it's not like you're comparing like a mass car CNN or something like that versus this, right? Where there's a significant jump in percentage. Pretty much ballpark same range, all these guys are.
Yeah, that's where.
Can I just go back a little bit, because you are all discussing about the head, all right? This is the figure 4 shows the last part, the ending part. During the middle, like the multiple fusions in the middle, they don't. I don't believe they stack they don't stack the different representations. I think he sums the different representations on the same scale after downsampling and upsampling, and then keeps the same number of channels. But I don't know how he does that. It's on section 3.2, but I didn't quite get section 3.2.
Isn't that kind of dependent on the task though? Like the head keeps changing for whether it's classification, object detection, post detection, or segmentation. They have different heads for the 4 of them. They don't use the same head.
Yeah, I'm just talking about. I'm just saying this is like the head, but the head of the HRNet, but it's not the ending head. These are what you were discussing here. The representation head, right? And this is different. What I'm seeing is that's different from the fusions we do on the middle, on the middle part, all the fusions, because we start from one. If you see figure 5b, we start from one representation and we end with the same number of channels at the same size, right? So we don't stack anything here. Or maybe he's. No, don't know. Maybe he's.
Go ahead, Antonio.
Well, I think he doesn't stack. He only sums the values on. Or he stacks and then do a 1-by-1 convolution to get back to the same number of channels from the branch, from the branch. But I'm not sure.
I forget. Let me a minute. I think this was the code that Rekil you had shared before in some other thing, right? So if we'll look at this in a minute, but once we get a little bit more understanding of the questions, and this one seemed to at least show the details of what happens in the parallel streams. We'll get to that in a minute once we get done somewhat with the high-level diagrams, because that will give us then a set of questions that can then be answered by diving into this picture of the code that exists. So here, I think
and just one last thing. On section 3.2, he says that the two-strided convolution just downsamples 2 times. So we were correct. It does a downsampling of scale 2 from the high to the medium branch, and then downsample with scale of 2 from the medium to the small branch, and then when he downsample at each level, he multiplies the channel size by 2. So that's why it's 1/4 and then 1/8 and then 1/16. He says
right
there.
And so that's why I was saying that 1 stride to 3x3 is 2x downsampling, and in order to go from yellow to orange, you will do 1 stride to 3x3. But in order to go from yellow to pink, you would do 2 strides to 3x3. And in order to go from here down to this red color, you would do 3 strides to 3x3.
Oh, I see.
And so that's kind of what's
clear.
Being referred to here.
That's clear.
Right. So, and this is where I thought, in HRNet v2, you do the bilinear upsampling, and you do the upsampling without changing the number of channels to the high resolution. You concatenate the 4 representations. So you do the bilinear upsampling, you concatenate, so you get this thick sandwich of 15C thickness, because it's 8C, 4C, 2C, 1C. This smallest resolution is 8C, then the pink guy is 4C, the orange guy is 2C, and the yellow guy is C. So 8421 is 15C, and then followed by a 1x1 convolution to mix in the 4 representations. Right, so that's kind of what I was pointing out and what Rachel was mentioning, why we mix in the 4, because as Rachel just highlighted to us, in this particular case, meaning in HRNet, we have the 4 scales and we carry forward the 4 scales, so we have the image and the information that's available to us from the high resolution and then C channels, whatever the next thing, medium 2C thickness, low 4C thickness, and smallest 8C thickness. And then behind this, we do a 1x1 convol to mix in all of these things. So now we come to the instantiation, and that's when I think the other window would be interesting to go through. So, this is the resolution thing we talked about. So first we take in the input data, apply the stem, go to 1/4, and then after 1/4 you go to 1/8, then 1/16, and then 1/32. Now here he talks about the stages, and I'll switch right after reading this paragraph to the other picture. So the first stage contains 4 residual units, where each unit is formed by a bottleneck with a width of 64 and is followed by a 3x3, which changes, changing the width of feature maps to C. Then there is a second, a third, and the 4th stage, and it contains 1, 4, and 3 modularized blocks. And this is what I was trying to align with the picture that Raquel had said previously. And then each branch, which goes in parallel in the multi-resolution parallel convolution, contains 4 residual units. And then each unit contains 2 3x3 convols for each resolution. where each convolution is followed by what Rick was saying about, what Jeremy does, which is every convol is actually convol bat norm value. So it's CBR, as I try to remember it, convolution bat norm then value. So what this description, which is, and sorry, one more thing before we go to the other picture, the width, which is, I wish he had called it thickness rather than width, but so I'm going to call it that. The thickness of the convolution of the 4 resolutions are C2, C4, C8, C. Okay, and hopefully, can you folks see this picture that I switched to?
Yep.
Okay, so this is the one that you had shared, and I haven't spent too much time staring at it. I tried to reconcile this, but if I screw up, jump in. But so this is the legend. It doesn't mean that this is the first thing that comes into it. This is just stuck here, but there's nothing in the branch 2 and 3. It's just an explanation of what is going on in the rest of the diagram. And it basically says that the 2D convol, this is what it means, that 3x3 convol, 64 is the number of output channels, followed by what is after the slash is the stride, and the padding, if present, is given as this number. So 3x3 called 64 by 2 means 64 output channels, stride of 2, padding of 1, and the filter supervised is 3x3, and then followed by bat norm value. So the stem, as we have discussed, is this. Then we go, then we apply a bat norm value, and then this is the very first stage. So this would come match with what is being done in the paper's yellow slice, if you will. And this would be orange, and this would be the pink, and then the red would be, I guess, the stage 4. So for the yellow, what we do is after we get the bat norm value, then we do this bottleneck layer. So that is basically a 1x1 followed by a 3x3 followed by a 1x1. And then in parallel, and this is the feed. This one, I didn't quite get why they have a feed forward direct as well, but that may be just the X plus, it's kind of the residual type of connection of 1x1 convol, and then whatever you get output here, you send it back after the batch norm. So that's the bottleneck layer, followed by, and this X3 or X4 says this block structure is repeated the number of times shown after the X sequentially. So that means actually there are 3 such blocks because it's an X3, one after the other. And each of those blocks is a 1x1, 64, 1, no padding. So this is just a stride of 1 in each of these cases. And that's yet another bottleneck layer, but repeated 3 times in sequence. And see, after each convol, there's a batch norm value after each convol. Right, and then once all that is done, you split, you do a 3-metric convol, 32, 1, 1, and then you transition 3-metric convol, 64, but observe a stride of 2. That's why you get the reduction and go to the next stage. So this, if I switch, is what we have done is executed until this yellow, orange, and we are at this stage. Is that correct, Vikram?
Yeah, I think that's my understanding too.
Okay. Now it gets a little interesting because this particular diagram is pretty condensed, but it actually corresponds to what is happening in the prior picture. This whole thing is shown by this diagram. So you go forward in parallel, but you also, or this whole stage 2, this guy here is what begins to create the pink block. So that corresponds, if you will, to when we begin to do this pinky, and all this does is all of the work to do that guy. So notice that there's from the orange resolution we go, or the medium resolution we go back up. So there ought to be a path there, and we also create a path from the high resolution to the medium, but also from medium to the high. And then of course we generate from the high resolution this pink guy. Actually the pink guy is a combination of from the yellow and also from the orange. So all that happens in this block in stage 2. So you can see that the generation of the orange is done here. And there is also this is why there are 2 directions. So there is, the upsample after the 1x1 convolve after the basic block. So the basic block is this guy, and that's what the basic block refers to. And basic block, again, the explanation is of a basic block is whatever a 3x3 convolve with, again, the layer number will vary depending on where you are in the pipe or the stage. And then, the number of times it's repeated is given here. And what he's saying is, you should look at the number that's provided 32 is not a given. So you do that basic block, which means it's actually times whatever, and the channel varies as well. And then there is a convolve to get it down, and then an upsample on the other way to feed it to the higher resolution path. So this is just a detailed diagram of what happens, illustrated by this guy pictorially.
So this basic block is basically a residual block, right? So
yes.
Normal residual.
With repetition, with how many other times you repeat as well. Meaning,
but
repeat meaning
the fusion again. Where is exactly the fusion part?
Here. And upsample times 2.
Oh, here I see fuse. And what does he do again? He upsamples and then uses this ReLU.
I think the BN upsample 2 means bilinear upsampling 2.
Is it some merge?
It's this guy. It's that guy. That arrow going up.
Yeah, on the end, does he sum? This is the critical part that I didn't quite get yet. He summed the upsampled version with the current one, and then use a ReLU activation.
What does he do? Yes. If you recall, what he shows here is a sum merge.
Yeah, it should be a sum because you're not changing the number of channels there, right? Your number of channels is remaining the same.
Yeah.
You're not concatenating.
Yeah, good question. That's buried in the detail, but according to this diagram, it's a sum merge. So and what's interesting is he batch norms this, and output of basic block is already a batch norm ReLU, and he sum merges it and then applies yet another ReLU.
Yeah, basic block is followed by a has a ReLU at the end, but that again goes through a 1x1 comp, right? Which is followed by the upsample merged and then ReLU.
Where is the 1x1 comp? Because here the basic block is this, right? So the output of the basic block comes out of a ReLU.
Correct.
Correct? So this guy is the output of a ReLU. Right? Now, here, this is an output of a batch norm.
You're going in two different directions, right? The right arrow takes you from left to right. So the basic block output that you were just pointing at right now.
Right. So there is a convol, there is a ReLU here, then a 1-by-1 convol, right? Then a upsample, then a batch norm.
Then fuse.
Correct?
Yes.
Then I'm saying the ReLU output of this is combined with the output of this batch norm coming down from this path, right?
Right.
And this is where the sum merge happens, followed again by a ReLU.
I see. You're saying there are two ReLUs there downwards.
Yeah,
I see.
because this output is already the output of a ReLU. And then you take this path, you sum merge according to that, and then you do another ReLU.
Yeah, I believe that's it. On section 3.2, he says that he sums the representations on the fusion. He sums the transformations of each representation, and the transformation is a simple identity when you are on the same branch, or an upsample was followed by one convolution.
One convol.
Or a downsample made by a two-strided, one-stride two convolution.
Right. One or multiple, depending on which level you're at, which stage you're at. Right. Yeah. So that's where, as you go down the stages, each of them becomes more convoluted.
Yes, for sure.
Multiple paths going multiple directions. But I think this picture captures it quite well if you're, because this gives you the next level of detail from this image, because the image is, somewhat simplified for obviously getting the level of understanding we first need, but I think the combination is a good point, Raquel, thanks for that. But this picture, the next level of detail of how exactly things happen is insightful as well. Right, okay, so in the interest of time, switching, so this is a level of detail that helps you kind of go through and implement the code at each stage, but you can see that it's quite complicated to keep all the channels and the stuff, but at the same time, there is a regularity to the structure of what they're trying to do. Okay, with that said, let's jump to the kind of the discussion of what happens. And then we also point out that in HRNet V2 and V2P, they combine, instead of just sticking with this high resolution part we already discussed, but they bring in all the other parts as well. That helps them in various tasks. I'm going to skip over, since that's not our focus. Let's just focus on segmentation stuff. And, they follow the random cropping and then random scaling. And
before that, Srinivas, the first, when he just started section 5, the segmentation section. I didn't quite get how he estimates the masks using only HRNet. You even comment that on the beginning of the paper, when he said he estimates the segmentation mask using HRNet, but I didn't quite get how does he do this with only those the backbone, the HRNet v2. He gets that 15 channel map as the
Right.
feature map, and after that,
Right.
I'm not sure how he gets the segmentation.
Yeah, after that, it's just a linear classifier with softmax loss to predict the segmentation map. So that's typical of what, I mean, that's just the standard way to go to the, you know, whatever your input image resolution is, and then based on the number of classes, you just do a softmax and your output is the number of classes. So that's equivalent to, let's see, what is it? DCHW?
Yeah, height by
That
width.
is, that's,
Yeah.
right? The number of channels being your number of classes.
PyTorch terms, yeah. Batch size, number of channels, which is number of classes, width and height. And then you just...
Yeah, so there you would have to go through, you know, after the one by one, because you do the one by one and then you put it to a linear classifier to get you the, and the reason for the upsampling by 4 is because you remember that the stem brought it down to 1/4. So to get it back to the original limit, you need to go back up by 4.
Okay, okay, I got it.
Once you've gone up to 4, then your channels are your classes. Right? So that's how it gets there. And then the metric in this case is class-wise intersection of intersection over union. Okay, and then now the one thing I didn't get in anybody, right? So Antonio, if you have, he says 6 scales. All the results are with 6 scales and flipping. Now, these 6 scales, what do these 6 scales now refer to? Because so far he's had 4, I thought. I mean, is it, or is scale something different that I'm confusing with the 4 stages that he has, or what the hell am I missing?
From my understanding, what scales was that you are talking about how you take the original image, downsample by 4, and then start off for the stem process, right? And
right.
then you have the 4 parallel channels, and that's where you're talking of the scales. My understanding of scale is that very input image itself, you start off with 6 scales. So let's say your very input image was 5112 by 5112. And then you take it at 6 different scales. I don't know how they choose what the 6 scales are. Or
yeah, no, they do. He does say that there is the, remember in augmentation, he says you scale between 0.5 and 2. So he might just choose 6 of those, randomly pick 6 of those is what, okay, now I get it. Sometimes when they just jump, then I miss the connection, but thanks, I think now that makes sense. So the 6 scales are 6 choices between 0.5 and 2 when that you use to scale your input image before even you start doing anything else.
Right.
Okay, got it. Okay. Yeah, sometimes when you're deep in the forest, you miss the forest for the trees. You look at the trees and you go, huh, what? Where am I? So I forgot what the scales were doing there. Thanks. Okay, so Antonio, did we address your question?
Well, I still didn't get the answer. You're right, because the 6 scale. How does he get 6 images on when he just get one segmentation map and at the end, and then upscale it 4 times? What does he get?
I think you run through, like, you take your input image and let us say you rescale it to 6 different sizes. You can automatically do that to your maps also. You rescale it the same way. Now you run each of these 6 images through your network. You will get a certain output. You have a certain scaled mask already, which you can compare with. So it's like basically, in other words, to put it is like, let's say you run everything at resolution, the same resolution. So let's call that resolution 1. So you run all your test images with resolution 1, compare it with your mask, keep your results for each individual image separately. Now you run for resolution 0.5 for all your images, run through your model, you have your corresponding mask calculated, do that 6 times for all the 6 scales. Now you'll have basically, for each image, you have 6 different results, right?
I
And
see.
you have 6 different values. I think that's what my understanding was.
Yeah, that would make sense. That you go through the pipeline for each image with 6 different what is it called, scales, and the output and the input are of the same resolutions, and so then you compare for the using the MIO method.
So the table for results are like the average of the 6 experiments.
Right.
Yeah, that's what I would assume. Let's go look at it, because that's what I was going to next.
That makes sense. Yeah.
So after reading all these papers that we have gone through, I think that is a really cool, like a test time augmentation stuff that Jeremy talks about. Changing the scales, especially for something like segmentation, object detection, or pose detection, where you really care about the scale. You know things are going to change with scale. Classification doesn't make it.
Yeah, I tend to agree, because that tells you whether you're able to observe images at different resolutions, right? Meaning objects, or detect objects which are small, which are big, relative to the resolutions.
Right.
Interesting. Thanks.
And the other interesting thing is they try to do this variation because of changing the resolution at the beginning itself, and they say that doesn't really help. See, just all the 4 high to low resolutions are added at the beginning, and the depths of the 4 streams are the same. The fusion schemes are the same, and they don't get the same good results, or at least they don't get as good as when you combine it after a set of convolutions and other processing. So by that, what is meant is, let's go back to the image so I can talk to it. I thought that was an interesting. So what they're saying is, instead of doing this pipeline for a while and then generating this and then doing that, resolving both in parallel for a while and then generating it, they generated this orange, the pink, and the red right at the beginning, and then went in parallel on all 4 parts, and then fused periodically. And what's interesting to me is that didn't give as good result as this approach. Again, the difference may be small, but it's interesting that experiment was less scoring than what we did here, which seems to suggest that combining after some processing is actually a better approach than just doing everything in parallel and just combining periodically. I thought that was an interesting aviation study.
I think the first one that you're comparing it with is like talking of taking it at different scales, right? Because you're downsizing right at the very beginning.
Yeah.
The way they have implemented it is like down the encoder path, you then kind of take this branch.
Correct.
And into it.
Right. Yeah. So that's why I was saying that it's like after you get to 1/4 from the stem, you just right away get to all, so right here, you generate the orange at this point. Right? And then you generate the pink at this point itself.
Right.
And then you generate the red at this point itself. And then you carry the 4 parts and then periodically fuse.
Right. And inherently
that doesn't give them
larger network than this one also, another.
Right. Yeah. But also it doesn't give them better performance, which I thought was interesting.
This is something which I just kind of realized now that HRNet, PSPNet, and DFlat, we never work on the original size of the image, right?
Sorry?
We did like we're doing 1/4. DFlab had that output stride, which was like 8, 16, or 32, and PSPNet had that feature map, which we reduced to 1/8 of the original image and then started. The only one which kind of does it differently is like unit, and there's no reason why we can't do it with the unit too, but at least the way we have seen unit, dynamic unit, they're not implemented like that. We start off with the original size image and we work pretty much with that, right? Just wanted
Yeah, so you're saying in any of the other three, you kind of have akin to the stem concept where you take it down to lower resolution, right, way to 1/4, 1/8, 1/32, something, 1/16,
right,
something, and then come back to an upsample. Whereas unit starts with and stays with the original image, although it also on the path back does the upsampling, but at least on the downward path, it doesn't go. It takes it through stages without doing like a stem type of thing. Is that the point?
Yep. That's a good point. So I'm saying like maybe we can also like reduce the computation on a unit. I don't know how it would affect the results by like instead of starting an image, start like feature.
I would think it will probably become a little worse than unit. See, that's where it kind of is like, again, it would depend on what metric you get by and what you're actually judging, what data you're using and stuff.
Right.
So, and then, the conclusions, but sorry, I think I skipped over the actual comparison of semantics. So, this is where they compare and then they say that, they do it for 3 different data sets: Pascal context, cityscapes, and then the LIP, which they show, unfortunately, the thing is differently there. And these 2 are the segmentation examples from cityscapes. Context, Pascal context is the middle 2, and then LIP is the right 2 with respect to semantic segmentation. And let's see, where are the results? Here. Here, this is Coco. Here, the semantic segmentation results, and you can see PSPNet, DFlat v3+. What's interesting is the fact to me that, in Icnr offline conversations, at least based on this, I didn't think it was that parameters were smaller, but they do claim later on I pointed it to the reference that they claim that it's less than MobileNet. And
yeah, I think the hidden thing there is that I think the network which they were pointing out specifically actually kind of points out to one of them was like a distal network. So I don't know if that is like a fair comparison, especially the one that we were kind of discussing offline. So yeah, if you have to do distillation, I guess you can do distillation all the others also. So there's nothing.
Yeah, that's kind of what I was saying too, right? So, but DFlat v3+, you can see the thing which is interesting though is the computation cost is like significantly lower, right? Even on a 48, which is the width, you see 65.9 million versus 43.5 million and 65.9 million. Sorry, I'm comparing wrong thing. The gigaflops 1444 and 2017 gigaflops for comparable MIOUs, and even if you say you got the same MIOU, you get like a third or a half of these 2. That I thought was interesting. It means you ought to be even, from a parameter standpoint, I would say comparable to PSPNet, slightly larger than DFlat v3+, but look at the comparison on gigaflops. There it seems like it ought to be much better. I mean, forget the scores. Let's say they're all the same. I mean, that's why I said between 79.6 and 81.1, while, it may be meaningful to SOTA results, I don't know whether on a particular instance and for the particular practical application rather than these data sets, whether you'll see the same results. I'm skeptical from what
also,
we've seen.
I just remember that, I don't know if you saw that on the author's presentation, but he like slipped, let it slip that he trained the HRNet on ImageNet, and it was slower than on using ResNet. I believe he was comparing like similar models with the same number of parameters, like he always does on the work, and I was intrigued because how does HRNet takes more time to train on ImageNet than ResNet if he always presents less gigaflops results on his tables here. Gigaflops are these gigaflops are like a measure of training, like training difficulty, right? Like training.
Yeah, see, as a hardware guy, I think it's miscommunication, if not deliberate confusion to compare flops rather than actual time. Because if you're just counting flops, it depends on the computer you're using, it depends on the efficiency, it depends on so many other things that you're hiding, but the only parameter that I would vouch or stand behind is actual time elapsed. And that's not what they show. So, I would take that with a pinch of salt, but I was just surprised at the relative numbers that they're sharing. Even if the thing is a wash, this seems significant, but on the other hand, it seems counter to what you mentioned. So that's somewhat confusing. And then,
he also says that. He also says that the implementation was not optimal for HRNet because he does a parallel computation, and actually the GPU, like PyTorch, doesn't do the branches in parallel. They do like sequentially. So maybe that's something like the reason.
Yeah, then, I have not dived into this OCR paper, which apparently is object context, something I forget now.
Representations.
That seems to provide object context in addition to the, other context that we have of scale and all that, which also helps semantic segmentation. And when you combine that with HRNet, then that's when they get really the best. But then again, what happens when you compare when you add OCR to PSPNet and DFlat V3? We don't know. So I think that's where the absolute best numbers, as Raquel already pointed out, are just, look at this. It's 81.6 versus 79.6. It's like a 2-point differential. And with respect to PSPNet, it's a 1.7 differential. And in fact, if you just look at HRNet V2, it's even less than that. It's only when you combine it with OCR that it gets even to the 2 points. And we're talking literally, 2 points, not 2% or something like that. So, and by the way, this is where I was saying random scaling in the range of 0.5 to 2. So that means he chooses 6 scales from that. And then substantial training of 120,000 epochs and so on. And by the way, we're close to out of time, but one thing I didn't have time and out of time to understand is the various metrics that and what they mean. I understand IOU, but I didn't, as I said, for lack of time, I didn't put effort into it. But if anybody else knows what the small IOU class and IOU category and small IOU category mean. I didn't look into what each of those things mean and how they are different from just an MIOU. Remember that this MIOU, if I'm not mistaken, he said was for class. Anybody else know?
Neither did I. Never seen that.
But it'd be interesting just to understand what these different metrics mean and how they are different from the MIOU, because this seems to be some kind of a sub measurement of the same thing per class, and then this seems to be per category. And what the category is and how is it different from class, I have no idea. Anybody else? My whole screen, anyone else know?
Nope, didn't even notice that. Yeah, good.
Yeah, that's weird. The weird part is class and category. Actually,
Right.
all of them are. Yeah, it might be something very specific with this cityscape dataset, cityscapes dataset. A couple of years ago, I had downloaded it, but I don't know if I still have it.
Yeah, and say, because it talks about the 4 metrics, and I was like, well, as long as we are in it, we might as well learn it. I'm sure I'll forget it 24 hours, but if you know it once, then it's easy to recall. The first time it's hard to just get it in your brain. Okay, I think any questions on this stuff? I just thought it was interesting from the point of view that it seems to get state of the art, but also, I mean, at another level, it also seems to be simple approach in that sense. Not very, so conceptually, not very different from dynamic unit in a sense, right? Because that also kind of takes you down the path and recombines it. But I guess the difference is you carry forward the parallel resolutions, the high resolution that you carry forward. But conceptually, you could say that you're carrying forward the high resolution even in unit because you pass it directly to the path when you're coming up. So all these seem to kind of point to the importance of trying to combine the high resolution precision of location with the semantic knowledge which you only get by going down to lower resolutions and convolving multiple times and stuff. So it's all creative, clever ways to kind of strike a balance between the two. And everything that we have seen seems to just try different approaches of doing that.
I had a...
Yeah. Thanks, Srinivas, for bringing up this paper. It was very, very beautiful and simple, and a simple state-of-the-art idea that gets really good results. Very interesting paper.
I had 2 questions. So one, he makes, there's like, I looked at his GitHub page. He has this claim that he expects this to become the backbone for everything.
Yeah.
And so it's like, okay, it works for, because I mean, it works for classification, segmentation, object detection, and then even pose estimation.
In fact, the pose estimation, this, I think, by the way, and also Antonio had posted this whole hour-and-a-half video. I haven't completed watching it. I started it, but I haven't finished it. And I'll post all these links on the channel once we're done. But there's a bunch of discussion this guy does, I forget, Peter, about how it's applicable to post detection as well. And that's where this code actually, that I pointed to, or the code explanations come from as well. Sorry, but your question, go ahead.
Yeah, no, it's just kind of interesting, like, because normally in the past, right, like say if you take object detection, like the person who's doing object detection is just focusing on that, and there's not one architecture for like object detection. So for example, like at work, we had to do some object detection. So there I chose RetinaNet, and because it just does this, and it worked really well. I have seen it work like really well in some really hard problems, like one on Kaggle and then even internally. Then for when I'm doing classification, I would pick like EfficientNet or or something else. But this is interesting that this one architecture, like for both object detection and classification, and it'll be interesting to just come. I mean, other than the standard data sets, it'll be interesting to see how it like starts showing up in Kaggle or other places. Because normally what I see is like you get a new architecture and people, like if there's a Kaggle competition, like there are 3,000 teams, they'll try every combination possible to get in the top 100. I should look some more. This looks very interesting, like the paper and how it translates to like other problems and domains.
Yeah, and also there is keep in mind that what's to me, I mean, the thing I did was just look at I think papers with code or something and said, oh, since they're doing this, let's see what the state of the art. And the top 3 state of the art results were what we discussed: Bilinear, DFlat, various versions, and then this HRNet. And HRNet, I think they even published the first, I don't know first, but more of it, like the V2 and stuff, this year, March, and another one in August of 2020. So the reason I bring that up is there also seems to be some lag between when a technique is published and when it becomes kind of widely used.
I see. Okay.
In Kaggle or other things. So in that sense, we have to keep that in mind. But I'm curious to see whether it gets taken up, as you say, in various domains. They do claim object detection, post estimation. That is kind of like the ResNet backbone, because at least in image processing, ResNet is pretty dominant in terms of its usage as a backbone in so many places. So that's a good thing to watch as to how, or is it just yet another, or is it significantly the dominant thing? Because again, that brings up this question, right? Like how, based on especially you and Steve, if you have submitted in other competitions, how widely prevalent are DeepLab and PSPNet, if you will, because they've been around a little longer?
In the steel competition, I haven't seen anybody using DeepLab. Everybody was just using PSPNet or UNets, basically. So DeepLab doesn't seem to have made it into segmentation competitions yet.
Again, like PSPNet and UNet are much older than DeepLab v3.
Right.
Like DeepLab v3, the very idea of like, I think the, what is that called, that we were looking at, the dilated convolutions, right? That itself is probably MobileNet v2, so around the time of, I think, when PSPNet or something came out. So yeah, the lag is very evident.
Yeah.
Talking to Mehul's point, I think that single architecture trying to do everything is, if you look at it, there are 2 kinds of classes, I think. Classification is one class, and then you can throw all pose estimation, semantic segmentation, object detection in another class. Classification, you really don't care where the object is, right? You only need to know something is present or not present. So scale really doesn't make difference. Whereas the other 3 kind of together, you need to know everything at a much more minute level at different scales and all that sort of stuff. Playing with it in a parallel sense like this, I think that's where they kind of win. But yeah, who knows what the adoption rate will be and how long it
will. That has so many variables, but it's a good thing to watch as to how, and of course there are multiple factors, as a guy who had to ramp products and stuff, with technology is just one piece of it. It's also how easily it can be adopted by people, how, the code, how it can be manipulated, how much the issues. I saw somebody pointing out an issue with one of the implementations in, I think, post detection. So how quickly do the authors or somebody else respond to that kind of stuff and fix it and make it, easy to adopt, manipulate, customize, add, subtract. All those things matter when it comes to adoption too. So, and whether it gets absorbed as something. I mean, if it gets taken up just as a hypothetical, as a fast AI backbone in something that Jenny does, watch out. Everybody will just use it, right? So it's also the library integration in some sense.
One last question. So if we have to say as an exercise, like if I just take his code and try to code it from scratch, like is that a worthwhile learning experience? Like, I mean, it would take a lot of time, right? Because one thing Jeremy says that even don't copy paste, just write the code out yourself.
Right.
Like I was thinking if that is if this has so many good concepts, if it's worth it to right.
You'd be trying to move it into fast AI, Mehul. That'd be a big win for it.
Oh, I don't know.
Yeah. No, I was thinking of an exercise like that, but I would need to, as Mehul said, because there is old diagram and all that kind of stuff, so it is very interesting. So something like that, you would learn a heck of a lot in doing an exercise like that, and especially I think the integration with fast AI, given, for example, Raquel, what you had tried even with, I forget, what was the data set you were actually using? I forget the name of it now. Camvid. So you can even stick with Camvid and then try to just implement for. Try to implement this in a fast AI context, I guess.
This architecture probably is one of the simpler ones, I think, compared to all the other stuff that we've kind of done. So,
that's what I was thinking. That compared to DFlat, I don't know, HRNet is okay, but this one is definitely simpler compared to DFlat v3+.
Right. So, I think that'll be a great exercise. I started moving it over then, got distracted with other things. But at some point of time, once I have that over, we can kind of look at that code also just to complete. My God, we've gone through quite a bit.
No, that'd be great. Whenever just drop me a note, and even if you're in the middle of some other competition, we can take time to just go through that, because that would be excellent. Yeah.
Cool. And then I just quickly looked up. So classes and categories looks like classes is like each and every specific detail. So like, for example, car, bicycle, bus, truck, train, motorcycle, caravan, trailer. These are all classes, but they all fall in one category called vehicle. So that's why you have less number of categories and more number of classes. That's the only thing I could quickly look at.
Okay, so category is a higher level abstraction than class.
And that small I probably points to instance, like instance segmentation.
The M is mean.
I could be completely wrong on that. I'm not sure.
Yeah, but at least the category thing is clear now. Then we have to just figure out what and the IOU cat, it's not the mean, so it's just that, and then the difference between small I and the mean IOU versus the small IOU.
I'm surprised that
because MIOU is also flat.
Is there nothing mentioned with the table that is not sure.
Somewhere in the paper they do touch on it, but they don't explain what the 4 metrics are. So I'm sure if we did an internet search, as I said, I didn't spend time on it, and if I find out, I'll post. But my rule of thumb is if I don't learn it when I'm in the depths of this, I will not go back to it.
I just posted.
So that's why
both of them seem to be there.
Sorry?
I just posted a link. That paper seems to have what IOU is and what we were discussing about cat class. So to address this, we additionally evaluate the semantic labeling using an instance level intersection over union metric. So that's what IOU is, instance level intersection over union.
So instance level would mean that if there are multiple instances, then you do it per instance. Is that what it means?
Yeah, at least that's what I understand with instance segmentation. Yeah, that's what that is, I think. So there are two persons, you don't categorize them as like one group. There'll be two separate instances.
Okay, so I think that brings us to the end of our semantic segmentation journey. It's been a long journey, but Mr. Bannister wins since I think he crossed the 90+ barrier, while the rest of us still lagged behind that. But I think thanks for everybody for sticking with it. I think at least I learned a lot, much more about segmentation than I ever knew. And hopefully some of it will stick by the time we return to maybe object detection or combinations down the road. And please do make your suggestions for the next one. And I think we have established several good methods that we have for validating. So think about, like, hey, does the submission work, blah, blah, blah. So I posted some suggestions just to get the ball rolling, but don't feel constrained by them. If you find other ones that are good, better, make the suggestions. And then next week, we'll spend the time kind of looking at each of them and why and what people want to do with respect and, things of that nature. And then maybe the week after, we'll try some submissions and stuff and kind of converge on which one of those. I think we've had experience with a couple of choices, and I think Mehul IP guided us out of one choice which wouldn't have worked. So I'm looking to all of you to help us make the right choice with respect to the next competition as well. So please make a suggestion during the week and then come join us next week, and we can look at them, spend a few minutes just looking at each of them, why people feel they're good or what are the pros and cons of the various choices, and then we can make the choice and move forward with them. And my rationale for also choosing an app is, several of us are in the Stanford class. We are kind of coming to the end of that. There are maybe 5 or more, 6 more, but very advanced applications, which and getting our hands dirty, so to speak, by diving into some of the implementation details as we have been able to do in segmentation would be a good way to actually increase our learning in the NLP domain. And, increasingly I find in medical AI or in other things, it's a combination of image and NLP and tabular. So potentially, after we are done with NLP 1 or 2, then maybe we choose combinations. But that's my rationale for trying our hands next at an NLP competition. So thanks, everybody. Any other comments or inputs from people? Everybody asleep by now?
Thanks, Srinivas, for this. It really helps with your comments on the paper and going through the paper in detail. Very helpful.
Great. Thanks a lot, folks, and look forward to joining you guys. I'll post many of these links on Slack, and please do make your suggestions for the next thing we turn our attention to. Appreciate it.